This is the first of two videos about capacitors. This video is some fundamental ideas and about discharging capacitors. So a resistor is a component that is designed to have a certain resistance. A capacitor is a component that is designed to have a certain capacitance. So what do we mean by capacitance? What is capacitance? And later on we'll talk about what capacitors are used for. So, most objects can store charge. Imagine like the ball of a Van de Graaff generator becomes charged. When we put a voltage across an object, or there's a voltage between an object and earth, then it becomes charged. And for the same voltage, if something has a larger capacitance, then it will store more charge. In the case of a big metal ball, then that will be the size of the ball will be the thing which will determine its capacitance more than anything. We get this equation C equals Q over V, our definition of capacitance. Q is the charge in coulombs, V is the potential difference in volts, and C is the capacitance in farads, named after Michael Faraday. So a farad is equivalent to a coulomb per volt. C equals Q over V. Usually, actually, we work out Q equals CV, more than using that equation. This is a capacitor. It doesn't look very much like it, but it's actually made up of two metal plates separated by an insulator. And we put a voltage across these plates, and one of them loses electrons and becomes positive, and the other plate gains electrons and becomes negative. Saying that, though, it's more useful to think about positive charge. Positive charge flows onto one of the plates and it becomes positive. Positive charge flows off the other plate and it becomes negative. I mean, current is the rate of flow of positive charge. Discharging a capacitor. This circuit here is a useful circuit to use to investigate the discharge of a capacitor. If the switch is initially closed, then the capacitor is charged, and there would be a current flowing through the resistor, but that's irrelevant. It's what happens when we open the switch. When we open the switch, then the capacitor will discharge through the resistor. How long will it take to discharge will depend on a few things. It will depend on how much charge is on it. It will depend on the capacitance of the capacitor, and it will depend on how much resistance there is in the circuit. We can think of a discharging capacitor. If you imagine a bucket full of water with a hole in it, a discharging capacitor is like a leaking bucket. The capacitance is the size of the bucket. The charge is the water in the bucket, so the current is the rate of flow of water. The resistance is to do with the size of the hole. If it's a small hole, then it's a large resistance. A large hole represents a small resistance. And then the voltage is the force which is pushing the water out. The current, the rate of flow of water, will not be steady. It will decrease exponentially. It will come out quickly to start with, and then it will come out slower and slower. So the rate of flow of water will decrease exponentially. So you cannot use Q equals IT. Q equals IT is for a steady current. This will not be a steady current. The rate of flow of charge, the current at any instant, is given by this equation. dq dt equals minus Q over RC. It's what we call a differential equation. And looking at this equation, we see that dq dt depends on Q, and it depends on R, and it depends on C, as we said earlier. Note that when the rate of change of a quantity is proportional to its magnitude, then this is a characteristic of an exponential decay. The other example of this we study at A level is radioactive decay. dN dt equals minus lambda n. The rate of change of n is proportional to n in radioactive decay. So the discharge of a capacitor, the charge falls exponentially. And all of these quantities will also decrease exponentially. The charge on the capacitor, the voltage across the capacitor, because Q equals CV, so Q and V are proportional to each other, the current in the circuit, which is the rate of flow of charge, and the PD across the resistor. As V equals IR, then the PD across the resistor is proportional to the current, so that will also fall exponentially. This equation, Q equals Q naught e to the minus T over RC, is an equation we can use to work out Q at any point in time. Q is the charge, Q naught is the initial charge, T is time, R is resistance, C is capacitance. And as I said earlier, these quantities will all go down exponentially, Q and I and V. This quantity here, E equals minus T over RC, it's useful to think of that as how much is left. At T equals 0, it will be equal to 1, and then it will fall exponentially and eventually reach 0. So it tells us the fraction that remains from 1 to 0. If you like, if you multiply it by 100, it would tell you the percentage left. Something else you should know, if we take natural logs of both sides of this equation and rearrange it as it's shown here, we get like a y equals mx plus c equation. And that means that if we plot a graph of log q against time, we'll get a straight line, and the gradient of the line will be 1 over RC. This is one of the ways you can find an unknown capacitor, is to plot a graph of log q against time and find the gradient. A very useful quantity is the time constant, torr equals RC. It can be measured in ohm farads, or it can be measured in seconds. What is the time constant? It's the time it takes for the capacitor to discharge from 100% to round about 37%. So from 10 volts to 3.7 volts, that time is the time constant. If you measure that on the graph, then that's a quick way of finding an unknown capacitor. If you divide the time constant by the resistance in the circuit, that would tell you the capacitance. So from 100% to 37% is the time constant. Similar to the idea of half-life in radioactive decay, half-life is the time it takes to fall from 100% to 50%. Here's a question you can have a go at. A capacitor discharges charged up to 12 volt, then discharged through a 20k resistor. Work out the following quantities. I suggest you pause the video and have a go at it. And here are the answers, and hopefully that's what you got.